Okay, so now we're going to move on to a different topic. We're going to start fluid statics, which is a study of fluids that are static and at rest. In particular, we're going to start off by trying to answer a very particular question, and that is, what is the relationship between pressure and depth, given that the fluid is at rest? Great. So the answer to those questions are relatively simple. We find out that pressure is equal to rho g delta h, where rho is the density of a fluid, g is gravity, and delta h is the depth within that fluid. And then we also get what I like to call rule number 1 of hydrostatics, which is that pressure, now this is a great opportunity to use active learning here. I'm about to write a sentence, so wait, let me write it out. You can always pause these videos, right? Let me write it out and then rephrase it in your own words, right? So pressure at a point is the same in all directions. Great. And that's exactly what it sounds like. You cannot have a situation in a fluid that is at rest where the pressure in one direction is less or more than a pressure in another direction. Now, that is not the case when you have a fluid in motion. A fluid in motion, you can have pressure gradients, which means that the pressure is higher to your left and lower to your right, or something like that. But in a fluid, static fluid, pressure has to be the same in all directions. And both of these are very important. We'll actually do a really fun example later in class where we see just how important this idea is. Cool. So let's try to prove rule number 1. And in general, in this class, I will not do a lot of derivations. I'm going to do a few at the start, more in depth, and then as we go along, the depth that I do the derivations in general will vary, but I want you to get comfortable with an idea of something called a differential element, right? And I think you might have used this in one of your other classes, but the idea is to look at a fluid element that is so small that we can make some very practical and useful assumptions about it. Now, we're going to use a differential element in this derivation, but not to its full utility, I guess you would say. All right, so we want to relate a fluid at rest and the pressure to the directions. What tool do we have that can relate pressures and weight? Well, we haven't given you any models really in this class, except for like a rough model for how shear stress works. So we're going to fall back on the mascot of mechanical engineering, which is sum of the forces and is equal to mass times acceleration, right? Which is the workhorse of mechanical and aerospace engineering. So here though, acceleration is equal to 0, which means we're dangerously close to becoming civil engineers. But the fluid is at rest, so acceleration is equal to 0. And if we have some of the forces if we're summing our forces, right, in general, we're going to want to draw a free body diagram. So let's do that over here on the right-hand side. We're going to draw a wedge as our free body diagram. So I'm going to draw the thick part of the wedge right here. And we're going to go over, draw the end, and then come down to the pointy side. Now we're going to draw in dimensions and things like that. So we're going to have a theta that describes the angle of this wedge. It is a delta x deep, a delta y long, and a delta z tall. And then we're going to, it's a free body diagram, we have to draw our forces. We're not going to draw our forces necessarily, we're going to just write our pressures for now, because we'll draw our forces, we'll write out our forces later. But we have a PS, which stands for P sloped side. we have a Py acting on the thick part of the wedge, and we have Px acting on the front and back of the wedge-shaped surfaces of the wedge. I don't know what to call it. And then from the bottom, we're also going to have a Pz, right? And finally, inside of here, we're going to have a Mg, a weight of our fluid pulling down. Now, when we have sum of the forces is equal to 0, we get to pick a single direction because forces are vectors, right? And we only care about forces that are in the same direction. So I'm going to suggest we pick the direction y and go to town with that. So this is our first equation. We go from 1 to 2, and we say that the sum of the forces in the y direction is equal to 0 is equal to, and then let's just write them out. So in the y direction, we have Py, and that's multiplied by an area. So Py multiplied by an area. And again, if we're doing active learning, here is an excellent chance for you to do that active learning, which is to say, pause the video and try to get ahead of me, right? Write out all these forces in the y direction without looking at the full filled out notes, because I am going to probably provide those too. So you want to do the hard work, right? And if you're doing the hard work now, it saves you time. Remember, we talked about 60% more retention if you do the hard work. Get engaged. Okay, so delta x, delta, not y, sorry, delta z. So delta x, delta z gives us the shape of, or gives us the area of this face right there. And then the only other force that acts in the y direction is ps, our sloped surface, and acts in the negative y direction. So we're going to put a negative py times, and the area of that is going to be delta x, delta s. But I'm going to write equation 3 here. We can write that delta z is actually equal to delta s times sine of theta. So we can substitute, oops, my bad, delta s, we forgot something up here on our top line, and this is sine of theta up here. Delta, because we want the x component or y component of ps, not just full ps. So sine of theta. So we take sine of theta and we now substitute this into that equation up there. So we get 2 plus 3 into 4, and we get that 0 is equal to py delta x delta z minus ps delta x delta z. And we get to do the most satisfying thing, I think, in your engineering classes anyway, and that is cancel out a whole bunch of stuff. And we find out that 4 to 5 py is equal to ps. And you'll notice there is no dependence on theta. So it is a scalar. Yep, so it is a scalar. What is another way of saying that something is a scalar? Use that when you're taking your notes, right? Put scalar, put a little note. Things that you add above and beyond what I write down and that aren't in my exact words will help your retention. Okay, so that's the rule that says that pressure is the same everywhere when fluids are stationary, right? And you'll note that one of the assumptions we make is that acceleration is equal to 0. So obviously when fluids start moving, this breaks down. But it doesn't matter what the slope is of this surface right here, PS is always going to be equal to PY, right? Cool. So what about delta P is equal to rho G delta H? How do we prove that that is true, right? Or at least is a good model, right? We'll talk more as the semester goes along about what makes a model good and what makes a model bad. In general, though, you're always making a trade-off between complexity and time and cost and accuracy, right? So when we do a derivation a lot of times the reason we do it is to highlight and to make obvious the assumptions and requirements that are needed for the system in order for that model to be accurate, right? That's why we do derivations. So in this case, we're going to talk about what makes a differential element, right? So we're going to use, to do this, we use a differential element, fluid element. And a differential fluid element is so small that this curved line, this parabola, across the differential fluid element, which has dimensions of dy, dx, and dz, across this differential fluid element, that line, sorry, that curved line looks straight, right? And if it's straight, if it is so small that anything varies linearly across it, we can do some amazing, the math becomes a lot easier, right? The math of lines is easier than the math of curves, which just seems obvious, but and let me show you why that is. So let's look at the relationship between depth and pressure using a differential fluid element here that I draw on the next page. We have the same dimensions as before. I'm not going to draw them because they clutter the drawing here. What we'll do though is we'll write out the full forces that are on this. We're going to do a full free body diagram, and that should be a clue to answer this question over here on the left. This question is what model can we use to relate pressures and gravity, right? And the answer is the mascot of mechanical engineering. Sum of the forces is equal to mass times acceleration, right? We're going to call that equation 1. And obviously, again, we do the civil engineering thing and make acceleration equal to 0. So here, now we have to do our free body diagram. We're going to draw in from the top. We're going to draw forces. I'm only going to do the negative direction of the forces because they're in front. But let's do the one from the top. We have a force going down, and that force is equal to the pressure in the middle. So one of the key concepts here is that we can define the pressure in the middle here, P, right? And then knowing that and knowing the dimensions of this box, we can define the pressure on the outside. So you know, the pressure in the middle plus dp dx, or sorry, dp dz times delta z divided by 2. And what is that saying? That is saying that from the bottom to the top of our fluid element, the pressure is obviously varying, right? And the gradient of that is given by delta, the partial of the pressure with respect to z. So since it's a straight line, if we want to figure out the amount that the pressure varies across that box, we just multiply it by the distance across that box. And this only works if it's a straight line. If it's not a straight line, then the slope varies and we have to do an integral. So we multiply it by the distance. We only care about the distance from the middle to the top. So we're dividing that distance by 2, delta C divided by 2. Okay. Now that we have a pressure, we need to multiply it by an area in order to give it a distance, right? Or sorry, in order to make it a force. So we multiply that by delta X and delta Y. Right. Same thing with X and Y directions. So I want you to try to fill out the X and Y directions now. In fact, fill out this whole thing. I haven't even mentioned an additional force that's going to be on this, although I did in the previous free body diagram. So try to fill that out before I do. Okay, so in the Y direction, we have the pressure. Again, we're always going to start with the pressure because the pressure is the same for all directions in the middle due to rule number 1 of hydrostatics. We're going to take that pressure and we're going to add, because we're going in the positive direction, dp dy times delta y divided by 2. And then we do our area, which is delta x, delta z. And finally, in the x direction, we have pressure plus dp dx delta x over 2 times delta y delta z. The last thing we need to add is, acting on this fluid element is indeed gravity, which is the mass times gravity, right? But in this case, we're going to use the density times gravity times a volume. And that volume is going to be just the dimensions of this box. So delta x, delta y, delta z. Great. What do we need to assume in order to use this then? Well, we remember, because we always start off, the next thing we do is our assumptions that we're going to use in order to solve our problem. So assumptions, assume, again, fluid at rest. And I always label my assumptions with letters so that I can reference them in my work later. Fluid at rest, and then you'll note that we've assumed that density and gravity are equal to a constant. So density is equal to a constant and gravity equal to a constant. That doesn't have to be true, right? Density can easily vary in a liquid. There's all kinds of examples of this happening in nature. Although for the most part, on the scale of human beings, it doesn't happen very often in a fluid at rest, right? So we'll make that be. Okay, so let's get started. We have 1, 2, 2, equation 2, and now we get to pick a direction because, again, some of the force is a vector equation. Before we avoided the z direction, and now we cannot do that. In fact, we're going to look at the most complicated direction, stare it in the eyes, and head right for it. So we're going to pick the z direction. Some of the forces in the z direction is going to be equal to, now we got to sum up all of our forces. So go ahead, pause, do that. And what we're going to say is we're going to say that negative rho g, because it's in the negative direction, right, times delta x, delta y, delta z, plus something that's in the positive direction. Now, we didn't write all of the forces, right? So there is on the left-hand side of this cube, there is a, on the back side, bottom side of this cube, we're doing the z direction. Oof. It's like I just went through all the names of my kids. Bottom side of this cube, pointing up, there is a force, right? And that force is going to be equal to the pressure in the middle minus, because we're going down in direction now, right? So we're going down, so we have to subtract dp dz, partial of the pressure with respect to z, times delta z over 2. And we're going to multiply that by the area, which is delta x, delta y. And our top force, which we did draw, is pointed down. So we're going to subtract that. And we say that minus pressure plus partial of pressure, partial of z dz over 2 times delta x, delta y. And that is, of course, equal to 0. And if you wanted to annotate things here, for example, you might put a b here to show that those are equal to a constant. You might put an a here to show that you did indeed cross that off and make it equal to 0. You could also put the a up here and show that that's why you made it equal to 0. Great. Now, since that's equal to 0, we get to go to town and do the fun stuff, right? We get to start canceling stuff out. So here we have a plus of pressure, we have a minus of pressure, so the two pressures cancel out. We have right, and that leaves a minus dp dz delta z over 2 and another minus dp dz delta z over 2 times delta x delta y. So we're going to combine those here in our next equation. So 2 to 3 gives us 0 is equal to negative rho g delta x delta y delta z minus dp dz times delta x delta y and delta z. And that's equal to 0. And we get to do the fun thing again, which is cancel out all the deltas, and we are left with and actually at this point we can take the partial and make it non-partial because there's no z, there's no other dimensions in this equation. The 3 to 4 gives us that dp BZ is equal to rho G. Oh, never mind, there's a negative there that I almost dropped, a negative rho G. And we integrate and we get that, if we do this integral correctly, we integrate here. We can separate, bring our Z over here, and we get that P2 minus P1 is equal to negative rho G H2 minus H1. Or, as it's usually put in the books, P1 minus P2, we're going to get rid of this negative sign here and this negative sign. P1 minus P2 is equal to rho G H2 minus H1, right? Which is, all that means to say is that the higher pressure is at the bottom where the lower height is, right? Cool. So let's talk about how these two models can help us predict behavior. We have a crazy set of tubes here. We know the height in the first tube and the rest are filled with water. And we want to know what is the height in the other three tubes and why, right? And you can't just say like intuitively, I know it'll do this. Great. I mean, that's one of the things we're shooting for in this class, is to give you an intuitive understanding of how fluids behave. But you also want to be able to back that up with reasons, right? And we have two models that we have learned for fluid statics. I want you to try to use those. So pause the video, draw what you think the fluid level will be in each of these the remaining three tubes, knowing that we've filled this and it's at static, the fluid is static, right? And then come up with the reason why. All right, let's try to do it now. I'm assuming you paused it after I told you to pause it. Now, you know what, from now on, I'll start being like, pause it now, and then we'll all know, because it's really weird talking to you and assuming you're doing things I have no idea if you're doing. Okay, so you paused it now, and now you start it up again. So the water has to be the same height in all three of these tubes, right? It's all filled with water. And the reason we know that all three of these tubes have the same height of water in them is two reasons. One is we can go from the top. We know it's atmospheric pressure at the top of all of these. P atmospheric, P atmospheric, P atmospheric, and P atmospheric. We can go down a certain pressure and we can find out the pressure here at pressure A, right? The way we do that is through P1 minus P2. P1 minus P2 is equal to rho G H2 minus H1, where this would be H1, this is H2. So this is, we'll call this P1. So we can solve for P1 using that, and then we use the first rule of hydrostatics, and we can go sideways in this fluid, and we know that everywhere at the same height in this fluid, the pressure is the same. Because they're at the same height, there's no reason for the pressure to change due to the density of the fluid. And the first rule of hydrostatics says that if we move to the right, the pressure has to be the same. So then we can go up in each of these cases, and we know the pressure at the top has to be P atmospheric. So we know the delta P that has to exist from this height to the surface. And if we know the delta P, if we know this, and the density is fixed, the gravity is fixed, we know the change in height for each one of these, right? And what's neat is that it doesn't matter the amount of fluid. It doesn't matter how thick the tube is or how thin the tube is, or the crazy path the water has to take. The height is what has to be the same, right? Cool. So let's learn about Pascal's barrel buster. And if you Google this, there's a fantastic video a physics professor did where she did this in real life. Now, it's pretty much been concluded that this was a myth that Pascal ever actually did this, but the theory is that, or not the theory, the myth is that Pascal came up with the relationship that we know right now, which is that delta P is equal to rho G delta H. Not so cleanly. Back then, they didn't really have, yeah, I think this was before the invention of units. So like equations looked a lot different back then. A lot of times they just said the pressure goes as the density times the height, right? And they assumed gravity was like just a constant that they didn't really know about at the time. But anyway, so he came up with this relationship that the pressure was only a function of density and height, and not a function of the width of a tube, right? And here we said it doesn't matter what the width is, the height is, the water's going to rise to the same height, and that's because the change in pressure has to be the same. So he was like, listen, width of the tube doesn't matter. And people were like, I'm calling BS on you. And he was like, well, all right, like let's do this. I'm gonna invent, I bet, given a tiny capillary tube, that I can burst a barrel. And people are like, ha, I don't think you can, because if you take that capillary tube and you fill it with water, you're gonna have maybe like, what, half a gallon of water in it. I don't know how tall this is going to be, but it's not much water. How can you possibly burst a barrel with half a gallon of water? They assumed it would take a tremendous amount of water to produce a tremendous amount of weight, and then that weight would burst the barrel. And so he did, supposedly, take a barrel, drill a small hole in the top, fill it with water, and then attach a capillary tube and seal it, and then he started filling the capillary tube. And if you watch the video online, you'll see what the difficulties in performing this experiment are and why I don't believe Pascal actually performed it. But we know that within this tube, the pressure, P1 minus P2 is equal to rho G H2 minus H1. So as H2 rises, where H2 is the, let's say we have 0.1 and this is 0.2, as 0.2 rises as we fill this capillary tube, the pressure at 0.1 is going to rise, because the pressure at 0.2 is always going to be atmospheric pressure because it's open, right? And eventually you're going to reach the yield, not the yield strength, I guess yield strength of the wood that was used to make the barrel inside, and it's going to crack. It's not going to explode because there's not a lot of energy in a capillary tube full of water. More importantly, as the water drains down, it's going to lose a lot of energy to viscous effects, which we'll get to. You'll enjoy it. So it's not going to explode. So all these stories of the barrel exploding are wrong, right? More like what happened is a little crack happened, and then water just started dribbling out like this, right? Or maybe even spurting out from that crack in a interesting but tiny little stream, but it's not going to explode. Now the video online, the professor did not use a barrel. She used a large glass container, and a large glass container will explode because when it fractures spectacularly and doesn't just crack in a simple way. So anyway, pressure is a function of height only, not the width of the tube, not the shape of the tube. We could have made this tube do something crazy like this. Well, I'm not going to try to draw a tube the whole way down. Actually, I am, and I'm going to succeed spectacularly. It's not a function of the shape or the dimensions or anything like that, except for the height. Pressure is only a function of height. Cool. All right, so in class, we will do a quiz, not quiz, and this is a fun quiz, not quiz, where we look at the difference in pressure at the bottom of a container of milk, where we have both either shaken or not shaken it. This is an old school milk, not homogenized, where the cream doesn't separate out. This is where the cream separates out, and the cream has risen to the top, so it obviously has a different pressure at the top. And then after we're done with that in class, we are going to do we're going to do our first problem in the semester-long design problem, which is the question of, can we have a single pump at the bottom pushing water up to the top and to a jet at the top, which is providing our thrust. And now every time you're an engineer, people might ask a question to you like that, and you as an engineer have to convert that into a much more precise engineering question. And so what we're going to ask is, well, what is the pressure at the bottom of this tube here that is needed to raise the water all the way up to the top, right? And we only have one model to do this, and that model is our hydrostatic model. And this is not hydrostatic water, but we're going to talk about what results when we use a model and we don't honor its assumptions, right? Great. I will see you guys next video.